Good morning, everyone. So today it's our last class, last meeting, and we're gonna go through this exercise here for imagery stability. I'll tell you more about that in a second here. I just shared this partial script on GitHub, so please make sure you download that last version of GitHub and move this script. It's called 0429 imagery stability partial. I just want to ask you to move that into the code folder of this current project. You do not have to create a whole new project setup. Just going to finish this one here. And before I introduce this topic, we are basically going to do something we have already done before. And I didn't there's not going to be a lot of new coding. I don't think there's going to be no new coding in this exercise. So really, I'm going to be asking in each step for each one of you to help me to develop this code as we move forward. All right. So let's get started with that. I know you're probably still downloading the script and moving it into your folder, but we're just going to have a little bit of introduction here before we get to that. So I hope you have enough time. All right. So if we just take a couple of steps back and look at the overview of what we've done on the previous exercises, we basically downloaded all the imagery for each growing season for 3 different years. For each one of those years, we summarize all those images, which range from, I guess, anywhere from maybe like 40 or 30 images to over 70 images, I think, were the kind of the range of images we had in different years. We summarize all those images by extracting the median value across the growing season for that year for each pixel, right? And we are assuming here that if the median green NDVI of a pixel across a growing season, if that value was higher, that area that pixel is in represents an area of higher yield potential compared to areas that had a lower green NDVI median across the growing season. So we're making that assumption here. And this again is to come back to the point that, you know, if you either don't have your monitor data for that year, for that crop, or even that crop overall doesn't even have this type of technology developed, you may still use imagery to get you some idea of different potential yield potential areas of your field. So we've done that on the last exercises. We finished extracting the median value for each one of those 3 years. So 2017, 2019, 2020 for this field. Now, if you think about it, so we have a median map for each one of those 3 years. This is pretty much where we were when we had the yield monitor data and we processed all that data and we have 3 years of yield data. It's the same place, it's just a different information. So what I want to propose we do today is that we use this imagery-based NDVI data to create a spatial temporal stability or variability analysis, just like we did for yield, right? Again, with the goal here, especially if we are trying to understand yield variability, if we don't have yield data, can we use imagery to get some insights into that? So that's the goal. That's the last thing we're going to do in this class, is to first create the spatial temporal, I'm calling yield stability analysis, even though it's not yield, it's imagery. And then we want to compare this green NDVI based spatial stability map with the yield-based spatial stability map that we did actually using yield data. All right, so I left you here all the packages, so just go ahead and run that. Okay, so if we think of it, if I want to do a imagery-based, I guess I'm calling yield spatial temporal stability, although it's not yield, it's imagery. We need 3 layers, right? So we need the layers that we produce less exercise, which we save them to file. So let me ask here, as I was saying, I'm gonna be asking different people to help me with different parts of the code. This is nothing here is new. At this point, you should be able to do this on your own. And so I do wanna ask for help. Let's see, let's start online today. Maybe in Tifton. Clint, what do you think we need to have here if I want to bring in the so the map we created with the median green NDVI for 2017? What would you type here?
Would it be a read? Would it be read stars and bring in that GeoJSON?
Well, let's try that. So, I mean, why don't we all just go ahead and type it? So read underscore stars. And then, so we have to navigate. I think we exported to the data folder. Let's try that. Yeah, so it would be that first one, right? So let's try that. Okay, so it did not work. And I don't know if the actual error message is really useful here. I don't think that is really helping us to understand what is going on. But can someone maybe suggest why this didn't work? Or maybe even you, Clint, do you know why this didn't work?
Would it be a CSV instead of stars?
We can try. That's the beauty of it. We can always try and see what happens. So I think actually it may have worked. Let's see. I mean, it did import, but it's not really what we wanted. All right, you're getting close. What do you think is going on here, Clint?
I would assume just trying to tell it to read the wrong thing or read it the wrong way.
Okay, so let me see if someone else can help Clint here with how can we fix this code?
To read the JSON, we need to use SF.
Yes, was that Hejimar?
Sorry?
Yeah, okay, awesome. That's it, Hejimar, thank you. Yeah, so this is a GeoJSON, right? So JSON is a vector file type, and in R, we treat that as an SF object, so it's just a read function, right? So we just need to read SF here, and that should do the trick. Thanks, guys. All right, so as we bring that in, at least on my side, I have 44,930 rows, where each row is a cell or a pixel, if we think of that in that way, where we have a pixel ID, a green NDVI value, and the geometry. If we check the first panel here, it is of type polygon. It is WGS84, UTM zone 16 north. So all that is good. All right, so we did that for the first year. If we want to do the spatial temporal analysis, we need for all years. So in the next chunk, yeah.
Can I just recap? This is in data folder. Data folder we have pixel, median, GeoJSON, and in output folder we have median, GNDVI median. The median one was for all the data. I just forgot.
Yeah, no worries. So, okay, so first off is on the output folder, we have similar names perhaps, but they're different file types, right? So what do you think is this file type here that we have on the output folder?
Oh, this is just 1 year, but.
So on your side, maybe why don't you click on one of those and tell me what you see?
Yes, it's the average, I mean, for all, one singular year, but we did for all the dates.
Right, but so, but what file type is this?
It's a, PNG, it's a picture.
It's just an image, right? Yeah, so this is just like, it's just an image, so this doesn't actually contain the data, right? So the data is what is on the GeoJSON on the data folder, right? Well, they are this, I mean, they have the same information behind it, but one of them is just an image, right? So, yeah. But so, yeah, so just to recap, so on the previous class that we did all 3 years together and we exported to data. I mean, we did all 3 years in the same class, I guess that's what I meant by together. We exported the 2017 pixel median, 2019, 2020, and they're all coming from different years with different images, right? And so we did for each individual year exported the median value of that year, right? And we are again assuming that that median value has some relationship with the yield potential of that year, right? And so now, if you imagine, this would be equivalent for us to have the 3 yield maps, right? And now we want to combine them into one and do the stability analysis. Yeah, does that clarify?
I'm just extracted one single day. It's not one day. All the days.
Yes.
On
So if you remember, there was that map we had like, so think if we go into 2017 and you have date on the x-axis and green DVI on the y-axis for 1 pixel, we had that 1 pixel kind of going up, and then we got the median on the y-axis of that pixel, and then we did that for all pixels of that year. So that's what these median GeoJSON are. Yeah. All right, so so the next step here would be to extract that for the 2019 year. So let me ask, let's see. Kumar, are you there? Awesome. Kumar, so how would you bring in the Pixels 19 data? What would you
I
type?
think we're gonna follow the same process that we did for 17, read SF.
So read SF. All right. And then get outside,
Go out to the,
roll in data, 2019. Awesome. So we bring that, if we print it, it's gonna be, is that a little bit different? Well, it seems like on my side, the 2019 has 3 extra pixels for some reason. And then we have, again, PixID, gradient DVI, and geometry. All right. And then next one is just gonna be for the 2020. So let's just go ahead and do a read SF. Get outside of code, go inside of data, and bring in the 2020. And again, all these 3 files here we created as a product of last class. All right, so also seems on my side at least, I have 3 fewer pixels on 2019 compared to 20, or I'm sorry, on 3 fewer pixels in 2017 compared to 2019 and 2020. All right, so next step here is basically just to combine them. Oh, you know what? There's actually one problem here. Because, so if you remember, to do this spatial temporal analysis, we have to have one object with a column of gradient DVI for each one of these years. So right now, I don't think that's gonna work. I mean, we have to basically join these 3 objects into one. But right now, I don't think it's gonna work because they all have the same gradient DVI name. So we need a way to differentiate that column across the different years before we join them. So how can we do that? Ujwal, what do you think? So right now they all have this column called gradient DVI, and I need to combine all of them in the same data frame with one column of gradient DVI for each year. But if they're all named the same, it's not gonna work. I cannot have 3 columns named gradient DVI. How would you fix that?
Make it longer. So we can stay.
Okay, so we are gonna do that at some point, but before that, like imagine we have to address the issue that they have the same column name. How can we address that? Rename, okay. What would you do here, Neva?
Maybe GNDVI equal GNDVI 17.
Yes, let's try that. So I do want to propose that instead of, we could use rename. I want to propose we use a dplyr select instead, and then we just select the green NDVI and the geometry. And then we, on the same step of the select, we also rename that column. So I want to leave PixID behind. I don't need that anymore. So Neva, you were saying to do something like GNDVI equals GNDVI underscore 17, something like that. Let's see if that works. Okay, it did not work. It's saying that column GNDVI 17 does not exist. What's going on here? What did you say, Doug?
Yeah, the 17 is good.
Right, yes. So the key here is that the new name you give it should be on the left side. So the new name on the left side equals to the current name. Yeah, so that would fix it. So if we do this and you print it, now we left PixID behind, we have GNDVI 17 and then the geometry. All right, so let's just repeat that for the next 2 years as well. Let's give it a pipe, dplyr select. Again, we're gonna say GNDVI underscore 19 equals GNDVI. That worked. And then the same thing for 2020. So give it a pipe, dplyr select, GNDVI underscore 20 equals GNDVI. All right, so now we are ready to merge these. I left you the code already. We've used this code before. So we're doing a join that is of 3 geospatial objects, 3 vector objects. I am starting here with pixels 19 instead of pixel 17, because at least on my side, pixels 19 and pixels 20 have the same number of pixels, and that is 3 more than pixel 17. So pixel 17 has 3 less pixels. If I start with pixel 17, then basically pixels 19 and 20 are going to have 3 fewer as well as we do the left join. That's why I'm starting with the one that has the most. So here it could be pixels 19 or pixels 20 will work similarly. So I left you the code here. We're just doing an ST join. We're changing the join type to be ST equals because again, these are supposedly all overlaying, all the pixels across 3 years are overlaying among themselves. And so this should work. If we run this, and we printed, now we have 44,933 rows, which is what we were expecting. I always want to remind you, when you do any type of join, it could be a spatial join with ST join, it could be just a left join with tabular data that's non-geospatial. Always make sure that your final number of rows is matching what you would expect, because if it's not, then something happened, and if you ignore that, it will impact whatever you do afterwards. All right, so what we have now is a column for GNDVI 19, as that was the first object that we started with the join, and then the geometry for that, and then we have GNDVI 17 and 20. So everything we needed here to calculate, to do the spatial temporal stability analysis at this point.
So for the 17, you would have 30 NAs. If I was 10 last time, the first 10 I'm not off.
Yes, so for the 17, we would have 3 NAs. In my case, they're not coming up as the first ones, at least 3 NAs based on my data. You all may have a different number of NAs because of the boundary difference, but we can even come here and just, if we just plug in a summary here after the pixels all, just so we inspect that. Yeah, in my case, I have 3 NAs on GNDVI 17, as we would expect, because that came in as 3 fewer cells than 19 and 20. And I don't have any NAs on 19 or 20.
Question,
Yes.
is there a reason that we joined 17 and 20 to 19 rather than doing rather than chronological order? Was there a reason that we chose 19 first?
Yeah, so the reason there was, so as I brought in on my side, and this again may be different on yours, but on my side, so 2017 Pixels 2017 has 44,930 pixels. And both 19 and 20 have 3 more pixels than 2017. So because we're doing a left join, which means whatever appears first is on your left side of that left join, and we are joining to that. So if we were joining 19 and 20 to 2017, then those 3 extra pixels that 19 and 20 do have would have been dropped, because the frame that we're using to do the join is 2017, which has 3 fewer pixels. Of course, in this case, 3 pixels is not gonna hurt in any way. If you lose 3 pixels when you have almost 45,000, but just for us to keep those since we have them, that's why I started with 2019. It could have been 2020 as well, right? Because that also has the 3 extra pixels. It's just, I guess the key here is just to not start with pixel 17, because that would force 19 and 20 to drop those 3 pixels that 2017 does not have. Does that make sense?
Yes, sir.
Awesome. All right, so now we have all the 3 columns we needed. Now we're going to do the spatial temporal stability analysis here. So let's start here, giving it a pipe, or not a pipe, but an assignment symbol. Let's begin with pixels underscore all, which is the object that we just joined above. So, all right. So let me ask you all the following. How did we do this? If you remember, when we did, just in your head, what was the process we followed when we calculated the spatial temporal stability classes? If you can just walk me through the steps we took, just theoretically, what we needed here. Renelisa, what do you think?
So the exercise.
Yeah.
I think we calculated basics.
Okay, so mean or median of what?
Of the yield.
Okay, of the yield, but in what, for all 3 years a median, or for each year a median? For each year, right? Okay, so we did that. And then how do we use that in the exercise?
And then based on the percentage, I couldn't remember the percentage, but there's 30, there's no stability, instability.
Yeah. So before we got to that point, we had to use the median of each of the years somehow. Right, so you're correct when you said we have to extract the median of each year. But then what? Then what do we do with that median of each year? Doug, do you have any thoughts?
Do we have to somehow put all the median together from each year, have them all together to make one value?
So I guess that's not exactly the direction. Maybe Renelisa remembered? Mm-hmm. Okay, so we're gonna get to that point, but I think we're still missing a step. All right, so let's think about this. We calculate the median of each one of the years. What do we do with that median then? How do we use that in this analysis? Sandas, you remember?
Just use the median value for the calculating the mean for each pixel in standard deviation and the coefficient of variation for the each pixel.
Okay, so you just mentioned another step that we're gonna get there. And so what Renalisa said, calculating the median for each year, that's right. So Sandas said, then we need the mean and the standard deviation, and then we do the classes, all right? That's the workflow. We're missing still one step here. Okay, so we get the median for each year, then what do we do with those values? Where do they go into the equation if I get the median for a year? Anyone remember that step?
We need to do the coefficient of variation, Dr. Box.
Okay, so we will get to that point, Vinicius. I think Neva was getting to it. Neva, what were you saying? Yes, that is the step we're missing, right? So we use the median of each year to standardize everything of that year to that median of that year, right? So that's the step we're missing. All right, so that's the workflow. We get the median, we standardize everything by that year median value. Then we calculate the mean of the standardized value of all 3 years and the CV of the standardized value of all 3 years, and then use those to create the classes, right? So that's the workflow. All right, so let's implement that in code here. Let's give it a pipe. For us to calculate the median of each of the 3 years, now is where we're going to do the pivot longer as well that you were talking about. So imagine I want to have a column where I have all the GNDVI 17, 19, and 20 title under that, and then another column with the actual values. And then we can group by that column, get the median of that. So let's do a pivot longer. So really, I just want to pivot all the columns that contain the word GNDVI. So I can just say cols equals to, and then we can use this helper function that is called contains. So GNDVI, any column that contains GNDVI in their name, I'm going to pivot longer. So I can just run that. And for now, I want to do this just so we can print pixel step. So we have 134,000 rows. We have this column called name where we have all the previous column names of GNDVI 19, 17, and 20 and their values. So now we can just follow this by a group by. We're going to group by the column name, which is the one that has the different year data in there. And then we're going to do a mutate. So if you remember the difference between a mutate, doing a group by summarize, if you do a group by summarize, you will always expect to have fewer rows than what you had started. If you do a group by mutate, you're going to keep the same number of rows. You're just going to create a new column that is going to have a summary information, but is going to repeat that whenever it's needed to be repeated. So let's call this for a mutate. I want to call this median. We're going to say median equals to, we're going to ask for the median function, right? So we want to, I know this is confusing and I just want to clarify here. So the map we have now, the current data we have is the median of that year, right? And now I'm getting the median of the median values of that year. So it's going to start getting confusing, but just keep up with us here. And then we're going to get the, well, okay, let's stop. Don't want to make it more confusing at this time than needed. So let's go ahead and get the median of this column value. And I just want to say na.rm equals true because for 2017, we're going to have 3 NAs. So I just want to remove those first. If we run that and we print it, now we have this column called median. Notice that the median value is going to be a single value for a given year, right? So let's say first row here is GNDVI 19, and then fourth row is also GNDVI 19. You see how the median value is the same for that year. So this median is the same for all data coming from the same year, right? So now that we have this, we can standardize, as Neva was saying. So we're going to plug in here a mutate. I want to call this year underscore STD to mean that it's the year standardized value. And this is just going to be the current value, which is that pixel specific value divided by the median of that year, right? So it's going to be value divided by the median times 100, just so we get into a percent score. So if I run this and we print pixel step, we're gonna see that we have now our E standardized. So this now is in a percent basis. If you remember, our rules to determine if something was in it, whatever class it was falling under, was based on a percent. So more than 15%, less than 80%. Those are all percent, which now we have as our standardized value. So let's say even if all those years were different crops, which in our case they were not, they were all cotton, but if they were different crops, your standardized value would take that into account, right? Because you're standardizing by the median of that year. So what the NA, I think that those 3 NAs are just gonna be ignored at this point, because so if we, well, I'm sorry, not, let me think about it.
Because I still have a lot of since when they in a audience with that.
Yeah, so that's a good point. Because yeah, I don't think that they're gonna be those NAs are gonna be considered here. So really the difference that made was for 2019 and 2020 that we did not have the NAs, that pixel. Well, okay, so here, yeah. So if you just think through the NAs. So the NA for 2017 is still there. You had a median for 2017, but when you do this ratio, that becomes NA. So we have an NA standardized yield, again, or standardized year for 2017. But we still have for that pixel, the year is standardized for 2020, 20, and 2019, right? So whenever we take the average of that, we're still gonna get a value for those pixels. It's just that that average is gonna be based on 2 years rather than 3. All right, so now so we don't have a pixel ID column anymore. Because, okay, well, I guess let me just show you this. So we have the standardized value, and here's the year information. And the way that R knows which pixel, so let's say GNDVI 19, 17, 20, are these all the same pixel, just different years, or is it a different pixel? I really don't know at this point, but R knows because we have the geometry. So now if we group by the geometry, then we can ask for a mean of those, right? Because it knows that which geometries are or are associated with different pixels. So if we come here, give it a pipe, I want to group by geometry, and then extract the metrics that I think Sandesh mentioned. So now we're going to come here and do a summarize and get the mean and the CV for each one of the geometries, or in other words, for each one of the pixels across 3 years. So the first one I want to call is the mean. So we're going to ask for the mean of the year underscore STD. After that, so you can give it a comma right before the last closing parentheses. You can break code to make it easier. There is no function in R to give you straight out of the bat CV. So we first need to calculate the standard deviation and then calculate the CV. So the next one here, I want to call ST. It's going to be equals to the function ST of, again, year STD, the same as before. And then finally, still within the summarize, we can name the next one CV and say CV equals to open and close parentheses. Coefficient of variation is just dividing ST by the mean, and then get outside of the parentheses times 100. So this is what this is what we're going to do. Well, just thinking about it, I think we have to add here NA remove. So 2017 NA doesn't impact those 3 extra pixels. So let's just say NA remove equals true on the mean, NA remove equals true on the SD, and that should take care of it. So if we run that, and now we look at pixels tab. So now we do get and again, remember, if you have a group by followed by a summarize, you should expect to have fewer rows than you had before it. So we had 140 or 134,000 rows. I did a group by and summarize. I got back to the 44,933 on my side. And now I have a mean and a CV column that we're going to use to do the classes. If you just come here, let this pixel step summary go through, just so we can take a look at the summary here. If you remember, the rules that we used to create the classes were based on the mean and on the CV. So here we have the mean from 70 to 142%, the CV from 0.01 to 28%. If you remember, the thresholds that we use for unstable was a CV greater than 30%. If we keep using that value here, no pixel would be classified as unstable. Just wanted to keep that in mind. All right, so I left you here the next chunk, most of the code. So we're just gonna have to help me a little bit here. So we're starting with the pixels step, which is what we just did here for stability. And then these are basically the rules that or the conditions we had before. I just had a lot of 3 dots here for us to complete ourselves. So previously we had a 30% right on those first three dots, right? So right here, something was classified as unstable if it had a CV more than 30%. I want to propose that here we change a little bit that to a different value. So we still consider the CV, but we are less strict as far as how we would consider something unstable. So I want to propose we use the threshold of 15 instead. So 15, if something has a CV more than 15%, then it becomes unstable. Then if the CV is less than 15, so you can go ahead and change at the next line, and the mean is less than a given threshold, then we call that low stable. So that threshold here in our previous yield exercise, does anyone remember what that number was? What was that? 80, right? Yep. So we can keep using 80 here, because if we come back to the summary, we had a mean that was the lowest was 70. So, you know, there are values below 80. So if CV less than 15 and mean less than 80, then is low stable. Now let's go to the next line here. Again, if CV is less than 15, as that is our threshold we're using, and mean is greater than a value and lower than another value, then is medium stable. What would be the greater than position here? Still 80, right? So if it's more than 80, and then on our exercise, I think we used 120%, right? I want to propose we use a little bit lower, so we use 110 instead. Again, just to have more points falling in that medium stable, or having other points falling in other classes, I guess. And then the last one here is, again, CV less than 15 and mean more than what? What would you put there? 110, right? Oops, 110. All right, so if you fill in all the 3 dots, go ahead and run it. And I left you the code here for us to group by ST class and ask for the tally, so we know how many observations fell under each one of the classes. So if you run that, this is what we see. About 1,000 were high stable, low stable just 440. Medium stable was the majority, so 38, almost 39,000, and then about 4,500 as unstable. All right, so let's go ahead and plot this. The first thing I want to plot is the mean map. So let me just print this pixel step class just so you see what are the columns we have here. So we have geometry, mean, SD, CV, and ST class. If I want to plot the mean, what should we fill and color by? What is the name of the column we would choose here? Vinicius, what do you think?
I would use ST class on the field and mean on the color.
Okay, we can try that. So ST class on the fill and then mean on the color.
I don't think you can use both, to be honest.
Both.
Can we? Like field and color can you use for the same one?
Yeah, I think so. But which one would you choose then?
If you want to see the mean, I would use the mean on the field.
Yes, perfect, right? So we have mean and color or fill and color as mean. That would give us the mean map. So this is how that looks like. So we see that we have a larger mean. I think this is actually a grassy area. I don't think this is the true field, at least on my side. But so if we kind of ignore that, we still see higher yield or standardized, and not yield, right? This is not yield. I have to watch myself here. I'm saying yield, but a standardized value being higher on the west side and lower on the east side, and especially on the gullies of this field. So pretty similar to the conclusion we got when we did this with yield. Now, next, if I want to show the CV map, what should I have on fill and color if you're looking at this data frame? What do you think,
The
Kumar?
CV.
CV, was that Clint?
Yep.
Awesome. Thanks, Clint. All right, so let's try CV here. All right, so this is what we see. We have a lower CV on the west side, a higher CV on the eastern side, especially very close to the field boundary. I think that's probably similar to what we found as well with the yield data. And now lastly, if I do want to show the classes that we created based on the mean and the CV, what would you change here on the next gen? Heshimar, what do you think?
I think it's SD.
So the SD is the column for the standard deviation, right? So this is the one, but what I want to show are the classes. So which column here has those classes?
So class
Would be the ST class, right?
S class.
So let's just go ahead and change to ST class. And this is how that map looks like. I did leave you here. I don't know if this path is the same on your side, but at least on my side, this is the path to see that map when we did for the yield data. I want to pop this out so we have them kind of side by side and compare. So the colors here still, they mean the same thing. But what do you think, like, how is this? I guess, how would you interpret this when you compare both of them? Let me see, I think, Kumar, what do you think?
I'm not sure right now.
What are you thinking? So the one on the left is the one based on EO data. The one on the right is the one based on imagery data.
I guess for the yield data, it is more with more details with respect to the one we did from pixel data.
Okay, so the imagery one actually has a smaller pixel size, right? So and that's because just the resolution of the satellite, which was 3 by 3 meters. The yield data we did on a grid of 10 by 10. So as far as potential to show in detail, the imagery one has more potential. Right.
Okay.
Renelisa, what do you think?
I think they both have high number of pixels per stable
Mm-hmm.
class. And um, there are more unstable classes in the imagery.
Mm-hmm. More unstable, right, on this side here.
Higher number of low stable classes.
Yep, higher unstable, yep. Yeah, so I guess, overall, I think that if we see the majority of the classes on the yield was on the medium stable, which is also what we see on the imagery. Some of the parts where we had the high stable are at least like we have some speckles on those same regions or similar regions. So maybe there's something about those parts of the field that are helping it to be high stable. Really, the low stable is perhaps the one that is most different, right? So the low stable on the imagery side was basically just related to a gully, whereas on the yield side, we had some more pockets of low stable. And then also the unstable, like all this eastern side seems to be more unstable, and that didn't really come through on the yield. Overall, though, I think it's pretty good similarity, especially when we're talking about a crop like cotton, where just higher vigor does not translate necessarily into higher yield, which, if we think of other crops like corn, soybeans, peanuts, that would be more of a relationship there of having more vigor representing a higher yield. So overall, I think it's still pretty promising that if you have no yield monitor data, you can still get to a pretty similar place just with imagery. And that's pretty powerful. All right, so that's all I had from my side. I do want to ask you that before you leave, you do your student evaluation. If you have any questions, I will open up that, but I just want to give you time in class to do it. So we have 3 minutes before our class ends. I want to ask you to go and follow this link here. Give me your student evaluation. It's going to be really important for me to understand what you liked about this class, what perhaps you think we could have gone faster, slower, done differently, and I can use your feedback to improve for next year. So your feedback is really important for me, and I greatly appreciate it. And I want to give you some time to go through that. So please follow this link, fill in your feedback. After you fill in your feedback, I'm going to open here a GitHub issue for you to claim your attendance. So after you submit your student evaluation, please go ahead and claim your attendance before you leave. And in the meantime, if you have any questions, I'm going to be here for the next moment. And I guess our final projects are due May 1st, so keep that in mind. We will be entering grading things that still have to be graded and entering your grades soon. I'll let you know once I finish with that. So if you have any questions, if you think I got something wrong on your grade, we can visit and check on that. And I think that's it. So thanks everyone for this semester. I hope that you learned some good skills to apply to your research, to your work. And let me know if you need anything in the future. I'll be glad to talk and help you out in any way I can.